Okay, we're going to look at some review problems to prepare for our midterm examination. This will be the first of those reviews, which will be followed by other reviews that talk about other topics. So this first one really kind of goes back to the first module where we're talking about functions, properties of functions, and what those all mean. So if you remember what a function is, remember a function is some kind of relation which each x is going to correspond to one y. So each x is going to have only one y. So one x can't go to two different y's. So if we look at this first function, it says determine if this relation is a function. Well, I would say yes, it is a function, and here's why. If you look at each x, this x1, the 1 goes to 2, the 3 goes to -5, the 4 goes to 2, the 0 goes to -15. There is no repeated x that goes to different values. So there's no x that goes to two y's. Now let's just say that I wanted to make this not a function, because right now it is a function. So if I were to add another point, all I'd have to do is say, let's say I add the point 1, 3. So now that would cause this not to be a function because you have two x values, the same x value, 1 and 1, that go to two different y values. And that's a violation of our definition of a function. Okay, the second problem says we're going to talk about the symmetry of some graphs over the x-axis, the y-axis, and the origin. Now, obviously the easiest way to do this would be just to graph it on, say, Desmos or a TI graphing calculator and just see what the symmetry was. But we kind of want to use the rule of symmetry to kind of see if these are symmetric. So if you recall, if it's symmetric about the x-axis, then we know the point x negative y must be on the graph. So the y value gets reversed. So when we plug x negative y on the graph, it should give us the original graph back. For the x-axis, it is negative x comma y. And for the origin, it's the opposite of x and the opposite of y. So if I plug in these new points into the equation, if I get back the original, then it is symmetric to that axis. So for the first graph, we have y equals x squared minus 9. So I'm going to do each one of these separately. So first, let's go ahead and do the x-axis. Now the x-axis does not happen very often because that means it is not a function, but we can certainly check it. So the x-axis, recall, is x negative y. So if I put that into my function, I get negative y equals x squared minus 9. Well, this is not the same as the original. Now, I certainly can divide everything by -1 to try to make it look like the original, but this is just going to give me y equals negative x squared plus 9. So that is not symmetric to the x-axis. And that's not really surprising because no functions are. So let's talk y-axis. So the y-axis, remember the point is negative x comma y. So if I put that into my function, I'm going to get positive y equals negative x squared. So I replace the x with negative x. And now if I take negative x squared, that gets rid of the negative because negative x times negative x is positive x squared minus 9. Now that is the original. It's the same as what we started with, so this is symmetric to the y-axis. Finally, we could check the origin. Now if it's one of the previous two and not both, this is probably going to be no, but we'll go ahead and check it just to be safe. So negative x, negative y, so we get negative y equal negative x squared minus 9. Well, in this case, the x becomes positive, but the y is still negative. So we have the same problem as the first one. So this is not symmetric to the origin. Now, if I were to do a quick graph of this, you can graph it on Desmos, but I'm just going to show you that it would look something like this. It's a parabola. It looks something like that. So not really surprising that you can see that's basically the same on both sides of this y-axis. So that's why it showed there's symmetry with that y-axis. Okay, let's look at b. b is a little less known function. It's x cubed minus 3x. So I really don't know what that function looks like, some kind of cubic. So we'll go through the same test the same way we just did. So we'll start with the x-axis. And again, it's the same point. That's x negative y. Now remember, there is technically no y here, but remember f of x is the same as y. So you could think of this function as simply y equals x cubed minus 3x. So we have negative y equals x cubed minus 3x. The x's don't change, the y does. So if I try to get this back to the original, say by dividing by minus 1, I'm going to get negative x cubed and positive 3x, which is not the same. The signs are different. So this is no. Okay, same thing for y-axis as the previous problem. For the y-axis, we're going to talk about negative x and positive y. So that's going to become y equals negative x cubed minus 3 times negative x. So if I look at this, well, negative x cubed, negative x times negative x times negative x is simply negative x cubed. So that's different. And negative 3 times negative x is positive 3x. So that's also not the same as the original. So maybe it's none of them. Or maybe it's the origin. So let's look at the origin. The origin, remember, we're going to replace with both the opposite of x and the opposite of y. So that's negative y equals negative x cubed minus 3 times negative x. So that's negative y equals negative x cubed plus 3x. That's just like we did in the previous one. But now we have this extra negative. So if I do divide everything by negative 1, what will happen is you'll see that the negatives there cancel, and the 3 over negative 1 becomes negative again. And that is the same as my original. So that is yes. This is symmetric to the origin. If I do a quick sketch of this graph, we can kind of see how it's also symmetric to the origin. It looks something like this, if I'm not mistaken. So you can see if I flip it over that origin point, that this middle point here, you get the same graph. Okay, so for the next problems, we're going to look at this this graph here. We want to know find the intervals where this is increasing and decreasing, and label all extrema as absolute max or relative max or min. Okay. So first thing I'll do is I'll look at where this thing is increasing. So anywhere the function is going up, we'd say it's increasing. So it's going up in this area. So my increasing intervals would be, of course, from negative infinity to where it stops increasing here. Now remember, for these we always use the x value, so it's negative infinity to negative 2. And then it goes down for a little bit, but then it starts going up again. And looks like it's from 0 to 2. So we'll add 0 to 2 to our intervals of increasing. And then at x of 4, it starts going up again, but now it never stops going up. It just kind of goes up forever. So the last interval it's increasing is going to be 4 to infinity. So the other intervals, it's going down, it's decreasing, right, in these two little areas. So if I write where it's decreasing, it's decreasing from 2 to 0, negative 2 to 0, pardon me. And then it's also decreasing from 2 to 4. So essentially it's just the gaps where the first one was increasing, it's decreasing here. It also says we want to label all the extrema. Extrema just means highest and lowest point as max or min. Well, this one here is a max, but it would be a relative max because it's not higher than everything else. This would be a relative min because it's at the bottom, but it's not lower than any other points because down here there's points that go down forever because this keeps going. This is also a relative min because it's at the bottom, but there are points lower. And same idea, this is a relative max because it's at the highest point, but only in a certain region. So max is at the top and min is at the bottom. The second part, B, says, okay, I want to find the values of f of negative 6, f of 0, and f of 5. Now remember what function notation stands for. If I say f of negative 6, that means x is negative 6, and I need you to tell me the y value. So if I look on this graph at negative 6, the y value on this graph appears to be negative 4. So function notation, the number inside is always the x, and then the number you get out is the y, or the output function. So f of 0, so x of 0, I go down on my graph and I see that's at a y, it looks like of negative 3. And if I do f of 5, I go over here to 5 and go up, that looks like that's going to be at 7. So just remember when you're talking about these, we're talking about this is the x value inside and the y value on the outside. Okay, number 4 is going to discuss list the transformations applied to the function g of x equals negative 2 x minus 2 minus 4 from the parent function square root x. And then write the domain. So what I'm going to first do is I am going to just write this thing really large. So I'm going to write g of x equals negative 2 square root of x minus 2 minus 4. Now each of these things you see, because we remember, we start with this original function, f of x equals square root of x. So anything that's changed in the new function is something that's going to transform the original function. So this negative 2 is going to be a transformation. This 2 out front is going to be a transformation. This negative sign out front is going to be a transformation. Out here is going to be a transformation. So we should have 4 transformations. So the first one, always work inside the function first. So I would start with this guy first. This would be my first one. It's x minus 2. Now inside the function always moves the graph left or right. And it's always the opposite sign. So since this is minus, my first transformation would shift to the right by 2 units. So if I think of my original square root function, I'm going to move it right 2 units. So the next one I do, there's nothing else inside the parentheses. Now we have basically multiplying out front and subtracting, but we'd always deal with multiplying first. So we have this 2, so I would deal with this 2 second. So this 2 is multiply. Whenever you multiply something, that's a dilation. So this is a vertical dilation. It's vertical because anything on the outside is vertical. Anything on the inside is horizontal. So it's a vertical dilation by 2. The next one I do is, again, this negative sign out front, which could kind of be considered as part of the dilation. But remember, when we turn something negative, it is going to flip the function. So this is a vertical reflection. So that's going to flip it over the x-axis. And then finally, always what goes last is the shift up and down. So this is going to be a vertical shift down 4. Now, the other interesting thing this problem asks for, it says, okay, you've got these transformations, that's great. You could obviously graph it in with a graphing utility, but I want to know the domain. Well, remember the domain of a square root function is just whatever makes the inside of the square root positive. So I'm thinking, what numbers make x minus 2 positive? So if I actually want to write it out formally, x minus 2 greater than or equal to 0, that's x greater than or equal to 2. So if I'm talking all numbers greater than or equal to 2, that starts at 2, and I use the bracket that's included all the way to infinity. All right, we have one more transformation kind of problem. It says, given the graph to the right, vertically reflect the graph, shift it left 4 units, and shift it up 2. Identify the new graph. Okay? So this graph originally, if we look at this graph that's given is f of x equals x squared. But if you notice, it doesn't start in our 0, 0. It starts at minus 3. So this f of x equals x squared minus 3 is what we have here. So now what we want to do is we want to shift this graph left 4 units. So we're going to make it go left 4 units. 1, 2, 3, 4. So I'm going to kind of track this vertex point. So I went left 4. And then I'm going to reflect it. I'm going to flip it over the graph. So if I flip it over the graph, that's going to make this value at -3 pop up to +3. And then I'm going to shift it up 2 units. So if I go up 2, it goes to here. So this is my new graph, something like this. So this is kind of an odd one where you're shifting a graph that's kind of already been shifted. It's already been shifted down 3. So we're going to reflect it, we're going to shift it left, and we're also going to move it up 2. And quite honestly, this reflect the graph and this shift left 4 can be done in either order. It's the only thing you got to remember is make sure you do that shift up and down last. Okay, this problem also asks, what is the equation of the new graph? So, since we called this f of x, this is a little different. I'm just going to call, let's say the original function is f of x. So I'm just going to see what happened to it. So if you remember what we did was we first reflected the graph, so that's going to turn it to be negative f of x. We shifted it left, so shifting it left, remember, is going to add a value inside. So it's going to be negative f of x plus 4. And then we're going to shift it up by 2. So that's going to be plus 2. So based on this original graph, this essentially is what we would get. Okay, this last page is just talking about some different operations we can do on functions. So we're given 2 functions here, x plus 2 and x squared plus x. We want to find the following and state the domain of each. So the first one says we want to add the 2 functions together, f plus g. So the f function is x plus 2, and the g function is x squared plus x. If you want to make your life easy, just put them both in parentheses and then do whatever algebraic operations it would say. So this would be x squared plus 2x plus 2 when I add. Now the domain of this would be all real numbers because there's no denominator, there's no square root, there's nothing really to make it undefined. For the next one we're going to subtract, so same thing, let's go ahead and put the parentheses, so x plus 2 minus x squared plus x. So I would go ahead and I would distribute the negative sign. So that's going to be x plus 2 minus x squared minus x. So just make sure you distribute it to both of those things in the second polynomial. These x's cancel and we're left with 2 minus x squared. Now again, no domain problems here. Domain problems typically come in with fractions like we've seen in our rational function section. So we're okay there. The next one says f times g. So we're going to take the f function, which is x plus 2, and times it by the g function, which is x squared plus x. And again, this is just 2 binomials multiplied, so we'll just FOIL. So x times x squared is x cubed. X times x is x squared. Inner terms are 2x, and or 2x squared, pardon me. And the last term is 2x. So that's going to be x cubed plus 3x squared plus 2x. And again, this is just a regular polynomial, so there are no problems with this one, so the domain would still be all real numbers. Now the next one gets a little trickier because we have division, so we bring in some domain problems. It says f divided by g. So the f function is x plus 2, and the g function is x squared plus x. So this is the quotient, but now we have to think about the domain. So if I rewrite the denominator, I can rewrite it as x times x plus 1. So now if I look at what makes the bottom equal to 0, because we know bottoms equal to 0 are no good, well then I would have to restrict 0, because I can't put 0 in for x, and I also have to restrict negative 1, because negative 1 plus 1 is 0. So that is the first one and only one that has any domain restrictions. Okay, the next two are compositions. So if you remember a composition, f composed with g means we're putting the g function into f. And if we're doing g composed with f, it's f put into g. So the first one says f composed with g. So we're going to put the g function into f. So everywhere we see an x in the f function, so in the f function it's x plus 2, but instead of x, I'm going to write x squared plus x, which is the g function. So we're putting the g function into f. There's only one x, so we only put the function in one spot. So that's x squared plus x plus 2, which again is just a polynomial, so there's no domain restrictions to that. Finally, we have g composed with f. And remember, g composed with f, we're going to put f into g. Now, interestingly enough, in g there are two x's, so we'll have to put f into two spots. So that's going to look like x plus 2 squared plus x plus 2. So the x plus 2 just simply takes the x spot in the other function. Now if we do x plus 2 squared, that's x plus 2, x plus 2, plus x plus 2. So that's x squared plus 4x plus 4 when I FOIL, plus x plus 2. So that's x squared plus 5x plus 6. And again, the domain of this would just be all real numbers because it's simply a polynomial. Alright, the last problem on part 1 talks about an inverse function. So it says, consider the function f of x equal negative 2x minus 4. Find the inverse. So this is a really simple one, because you remember inverses. The idea how we find inverses, we switch x and y and solve for y. Well, I would first just write this as y equals 2x minus 4, because there was no y, and then I would simply switch x and y. So x equals 2y minus 4. I would add 4 to both sides, and then I would divide by 2. So when I switch x and y and resolve for y, I get y equals x plus 2 over 2. So that is f inverse. So f inverse is x plus 4 divided by 2. Alright, so I hope this is helpful. Please let us know if you have any questions.